And this will be single stage amplifier. So basically the common source amplifier is like this. So there will be a current source ID and a supply VDD. Our source will be grounded, this will be drain, and this is a NMOS. Let me call it M1, and we'll take output from here, Vout. Okay. So if we do a resistive common source, so our load will be resistive. So this current source will be resistive current source. Means we will replace this ideal current source with a resistance. Okay. So this will be RT VDD, and the current flows through this will be ID. And then we can say this is also a resistive load common single stage common source amplifier. So we'll design this one using GM over ID method. Okay, so let us design with VDD. Okay, so let us design this. So basically we'll design this one, and we'll use the GPD means 90 nm technology. We'll use 90 nm tech. Maximum VDD will be 1 volt, and our gain will expect a gain of AV equal to 10. Okay, and our UGB, unit gain bandwidth, so we have to check whether we'll get this technology by using our GMID method. Okay, so UGB will be 10 megahertz, that is unit gain bandwidth, and our output capacitance Cout will be 1 picofarad. Okay, so this is a 90 nm tech. So what actually we have formula. If we neglect the small channel, that is channel length modulation, so what we can say is, first point is our gain will depend on GM, that is negative because it is a common source, minus GMRT. Okay, so what we can tell that the required RD is equal to our gain divided by GM of the MOS M1. So this is M1. So I can write GM1. So another point, formula for unit gain bandwidth, that is UGB is equal to the intrinsic transconductance of M1 GM1 divided by 2 pi this Cout. Okay, so how much speed will be, means what is the maximum frequency this M1 can go? It depends upon the output capacitance and GM of that circuit. Okay, So from here we have what is C out, we have what is UGB, so we can find GM1. So we can say GM1 is equal to UGB into C out into 2 pi. So from this calculation we can get, we have expected it UGB of 10 to the power 10 into 10 to the power 6 and a C out of 1 into 10 to the minus 12 and 2 pi. So if we do the calculation, so we are getting a value of 63, around 62.28, so 62.8 microsiemens. Okay, so around 63 microsiemens. So what will be the RD value? So we can say that from here and this part we can say RD is equal to, we need gain of 10 and we need 63 into 10 to the power minus 6. Okay, AB by GM1. So if we calculate that one, we'll get a value of 159.154 K. 159.154 K. Okay, so we need this much of resistance and this much of GM1. Okay, another thing, we know that our V out equal to, so another thing we know that our V out equal to VDD. Okay, so you can see here, so from here the current will flow through this RD, some drop will be there, so voltage drop will be IDRD. So that much of volt, after that much of voltage, whatever you will get as V out. Okay, so V out equal to VDD. From VDD, from source the current will flow and some drop will be there, and after that drop whatever remaining part is our output voltage. So I can write that here, VDD minus IDRT. Okay, so we can find our V out and we know our VDD. Similarly we can find our, how we know our RT, we can find our ID, that is required current for this structure. So for maximum gain we'll find what the need of V out. What is the V out? Or V out is simply VDS1 here. Okay, so we need to find what, for what VDS1 we are getting maximum gain. So another thing, if we go through the gain part, FE, the gain is GM1 divided by total GM1, actually GM1 into we can say that, so let me write here. So if we include our channel length modulation, so we can say that our gain is minus GM1 R01 parallel with RT. Okay, so R01 parallel with RT. So for R01, what I can write 1 by GTS. Okay, so if I go to this one GM1, so this is R01 RT divided by R01 plus RT. Okay, so this is called minus GM1. R01 is, so I can write here R01, it is output impedance of M1 and it is denoted by 1 by lambda d, lambda id. So lambda is the factor that is small, that is channel length modulation, and IDs are current. So similarly, we can write that GDS, that is transconductance between drain to source, is equal to lambda ID. So simply GDS is 1 by R0. So I can replace R0 for R01 for GDS. Okay. So 1 by GDS1 into RT divided by 1 by GDS1 plus RT. Okay. So I can write like this: AV equal to minus GM1. So if I take common this part, so see, this is GM1 divided by GDS1, okay, RD divided by 1 by GDS1 plus RT. So here you can see, if I do the solution again, GDS1, that this will be GDS1 RD divided by 1 plus RD into GDS1. Okay, so this GDS1 will be cancelled, and we have minus GM1. So now if I take RT common from both sides, so RT divided by RT, so 1 by RT plus GDS1. Okay, so here we can see we have value that is minus GM1, RD cancelled, divided by GDS1 plus 1 by RT. Okay, from here if I divide ID everywhere, okay, so if I divide ID, so what happens? I'm dividing ID everywhere, so what will I get? Minus GM1 divided by ID, GDS1 divided by ID plus 1 by ID RT. Interesting fact is, from this equation, what we are getting, that is IDRT is equal to VDD minus Vout. Okay, so this IDRT can be replaced by 1 by VDD minus Vout. Okay, so this is now our gain equation. So if we find this AV versus GMID, AV versus GM over ID, then I can get a current, get a gain of 10 wherever I want. Okay, so now we understood what we need. We need for a GBW we need a GM of 63 micro, where RD, if we come to for gain of 10 and GM of 63 microsiemens, we need RD of 160 kilo ohm nearby, and we need a AV of 10, and we need a UGB of 10 megahertz. Okay, so this is the requirement. So you have to take, I have taken the length and width as variable. I have taken this voltage as variable. I have taken all these voltages as variable. Okay, so this is drain voltage, this is gate voltage, this is source voltage, this is body or bulb voltage. So let me launch ADEL. So we can get all the variables here, and I have taken this V in also variable. Okay, so what are the variables? My length, it is 100 nanometer, then VB. So since this is NMOS, our bulb will be connected to ground, so my VB is already connected to ground, so the variable will be 0 volt. What will be the drain voltage? We'll have to find that one. So let me, because I will sweep that, let me take it VDD by 2 initially. Same for VG, we'll sweep that to find the proper value. Vin we don't know till now, so I'm taking 0.5. And Vs, the source voltage, that will be connected to ground, so 0 volt. What will be width? The minimum width is 120 nanometer. I'm taking that one. So what I'll do first, I will do a DC analysis. Okay, and first I will vary my VD, that is drain voltage, to find the optimal drain voltage for my design. Okay, what the drain voltage I can take, so that my device will be in saturation as well as it will provide me maximum gain. Okay, so let me run it first, otherwise I cannot get the operating points. So I'll go to the calculator and I'll find the VD sat first, that is VD sat here. Okay, then I'll find GM over ID. Okay, then the gain, we need the gain, so we need the AV. For AV we have found a formula, that is GM over ID divided by GDS over ID plus uh, the magnitude of gain is plus 1 by IDRT, or 1 by IDRT. Okay, so here 1 by VDD minus V out, so VDD is 1, so I'm taking that as 1, but for GDS by ID. Okay, GM over ID gone. Now GDS by ID. Okay, now 1 divided by 1 minus VDS. Okay, so 1 minus 1 is our VDD and VDS is equal to V out. So this is 1 divided by that much. Okay, now I will plus the GDS by ID, and this is whole divided by GM over ID. So GM over ID divided by this much. Okay, so this is our what AV will be. So let me send it to VDS. Okay, what more I need? Actually ID, I need ID to check ID current. Okay, so this much will be done. Okay, so this is VD set. VD set. This is GM by ID. GM by ID. This is AV and this is ID. Okay, so I'll run. So mainly I need this one. So we'll take this AV to another window to see its curve, how it is varying or how it is changing. So from this curve you can see the maximum AV we are getting at this point. Okay, so maximum AV is around 320 millivolt of VD. Okay, so we'll set that, because if I change the channel also you'll find the same behavior. Let me do that. So let me change the channel length 100 nano to 4U or 5U, and you'll find the same curvature. Okay, you'll find the same curvature, except only this is the minimum length, and for other it is 400 m. So around 400 millivolt, all the gains are same. So what we'll take, 400 millivolt, and we won't take the minimum channel length. So what we are getting here, we are getting our VD. VD is 400 millivolt. So I am changing here 400 millivolt. Now since I have found my VD, I'll make it constant. I'll change VG to find all other parameters. For what channel we are getting our gain, that is 10 AV. Okay, so we'll vary our channel length and we'll vary our VG so that I can find the GM by ID. For what GM by ID we are getting our value. So for that, what we'll do, we'll plot all this with respect to GM by ID. Okay, so let me open this one and I'll take here. This is GM over ID and this will be our AV. Main important thing is AV or not till now. Okay, let me set that, and this is gain versus GM over ID. Okay, this one first one. Now next what I need ID versus GM over ID. So ID, here I have ID, I can change it, ID. So this is ID versus GM by ID. Okay, so what next? VD set or VGS and VDS. Okay, maybe done. VD set, we can do that one. Otherwise it is not required. VD set is not required. FUG required. Okay, so frequency required. For that we'll go to OS parameter and we need unit gain bandwidth. So this is our FUG, unit gain bandwidth, and let me do that. Okay, so this is UGB versus GM over ID. Okay, so GM versus GDS also required, but we can ignore that because we are directly taking the AV and we can find that. We are taking ID, we can find that current. So I think this is okay. This much will be keeping. No, this much will be fine. UGB IDFE. Okay. So I'll save all this and I will save, and I'll do a parametric sweep of length from 100 nanometer to 5U. Okay. Let it be 10 steps. So what I'll see, okay, so this all the changes are with VD, so it is not correct. What I need, I'll need the change from for VG 0 to 1. Okay, let me run it. So what I can see, for different VG value, you can find the GM by ID. Okay, so VD set, because we are this is important. So let me check, go here and send it. So our VD set VD is at 400 millivolt. So whatever VD set is below that, okay. So this is all VD set. So at 400, our VD is 400. Sorry, 400 millivolt, right? Okay, we won't go there. Don't worry. Our MOSFET will be in saturation, because you can see for VD sat 400 I need 578 millivolt of VG. Okay, so here if our gain is going somewhere, so what I need is gain of 10. So around 208 millivolt of VG we are getting gain of 10. Okay, if I am giving more VG, I'm not getting the gain of 10. So it is around 208 millivolt. So what is the GM by ID at 208 millivolt? 208 millivolt or less than that. 208 or less than 200 millivolt. So our GM by ID is 17. So we have to take that one. We cannot take 21. Okay. So 17, the lower GM by ID. So if we see here, the lower will be 17.6. So we can take this one. Okay, 2.2. Okay, 2.2 or 3U we can take the not no, okay, we'll take 2.2. 2.2U as the length. Okay, so for 2.2 length, what will be the FUG? So we have to check the FUG. Okay, so UGB, that is for 2.2. For this one, our GM by ID is 18, around 18. So 53 megahertz is okay for our processor, because we need 10 megahertz and it is okay. 53 megahertz. Okay, from this solutions that our VG will be 208 millivolt. Okay, that we have got, and our channel length will be 2.2U. That much we have got. Okay, so let's run again and see if our AV is meeting that one. So this is our AV. Okay, let me first check VG 208 millivolt. For 208 millivolt, our AV is 10.08 and it is 17.223 our GM by ID. Okay, so it is okay till now, and it is our VD sat equal to 100.5 millivolt, which is well below than whatever 400 millivolt we have taken. Okay, so this is done. Now what we have to find? We have to find width, and this width, what we have to calculate? We have to calculate GM of 63. So if we increase width, of course we will get the GM. So what will be the GM? GM will be 63 microsiem. So what we need here, we need calculator first, and we need the GM. Okay, so we need GM and we need GM over ID. GM versus GM over ID. Okay, so this is only GM apply, and this is GM versus GM by ID. So this two I need. Okay, so now I'll change VG. Okay, but with respect to width, I'll do parametric analysis with width. So I'll vary the width from 120 nanometer to somewhat 10 U to check what is the GM. So the most thing I need is this one. This is, and we can see that is all this width variation. So for VG208 millivolt, I need more GM, means 63. So maximum I'm getting is 50. So what I can do, I can increase. Let me take it to 20 or 30. Let me run it. And same at 208 millivolt, I'm getting 81. Okay, for this one. So let me check for which one I'm getting 81. Okay, so I'm getting at 16 micron, I'm getting 81. So from somewhere 10 to 16, 10 to 15 I will get. Okay, so let me find that one, like that. 10 U to 15 U, exactly. GM 63 to 65. Okay, 208. So 67 we'll take, or 64 we'll take that one. So, okay, so we'll take this one, and this is 12.78. Okay, so around 12 or more than 12. Okay, let's take 13. Okay, so for 13 what I can do, I can do 6.5 U, and I can increase the multiplier to 2. Okay, let me save this one. Okay, so let me run that one at 208. We'll see if everything is going well or not. So 208. So 208, we can see that our GM is 66, our gain AV is 12.75, and GM by ID. So here GM by ID is actually becoming higher. So we cannot take GM by ID that much. So what will change? We'll change the VG so that our GM by ID will be reasonable, below 10, because that will be a weak inversion. Okay, so here we have to check the UGB for 17, for 18, I guess, for 18. and our UGB is good. Okay, our UGB is good, our gain is good. So what we can do, we can, because our GM has changed here, so what we can do, we can decrease this one to 3.2, and let's see. So here, around here. Okay, so now we can see for 254 millivolt, that is 17.161 GMID, 17.161 GM by ID. So we are getting our gain AV10, we are getting good UGB, we are getting our GM expected. So all is calculated. So we'll take this one as our final value, 3.2. Okay. So our VG will be 254. Okay. And our V in will be same, 254. So now everything calculated, and we have already calculated the RD, this value, resistance value, and that resistance value is 160k. Now let's undelete this one and undelete this one, and let me check. So multiplier will be 2, our length is 2.2, and our total width is 3.2. Okay, so you can see here 3.2u, 2.2u, VD 400. So now this is our VD, so I'll change this VD because I have already calculated for our NMOS. So now this VD or VDD will be 1 volt. So I'm changing this one as 1 volt, and I don't need these calculations for now. Double plot, and I don't need this one. Apply. I need a AC analysis from 1 Hz to 100 megahertz. Okay, so let's see, this capacitance value is 1 picofarad. Okay, good. Okay, so 100 megahertz, and all these things are not matter now. These things are matter to 3.22, and this is 159 or 160. Okay, let's do a run. Let's check. Finger crossed. Okay, completed. Now I will plot a second phase. I don't know what will happen. Okay, so you can see 19.89 dB. So 10 means how much gain should be there? Around 20 dB. So I'm getting around 20 dB. Okay, and let me see if I'm getting more than 10 megahertz or 10 megahertz. Okay, so I'm getting 10 megahertz, no problem with that one, and I'm getting a good phase margin, 180 minus 95. So you can see I'm getting all this without doing much of calculation, only doing the GM by ID, using GM over ID method and LUT method, lookup table method. So if you like this, you can comment and subscribe to this channel for better videos. Thank you. So whatever the gain was, we have taken AV as 10. So in dB, AV in dB would be 20 log 10. So for We got this one, we got this one, we got this one, and we got this one. Thank you very much.